you can have your microphones off when you're not talking, that's great. We'll have the chat function open if people are interested in popping questions to the presenters in the chat, but we may not necessarily have time for lots of questions to each of the presenters, if that's okay with you. So I will hand over to Mark and team, and thank you very much to everybody for attending today.
Mark?
Yes, Colin.
Can I run the presentation from my laptop, because I've done a bit of editing.
Yeah.
I've been a bit naughty and done a bit of editing. Let me see if I just pull it up. Oh, hold on. I need to do that magic thing, don't I, where I share screen. This is why you should never let me do this. Excuse me. Right. Can everyone see what I'm seeing? Maulik and Jenny and Mark. Yeah. Okay. Cool.
Yes.
Should now see the slightly revised title page.
Okay.
I've gone full screen. Is it gone full screen for you guys?
Yeah.
Okay. Well, thanks Jenny for inviting us to present. I'm going to present a very short overview of the Green CDT on behalf of I suppose the grand PI of the Green CDT, which is Scott Heath. Scott can't attend today, but myself and Maulik Patel, University of Liverpool, are standing in. Maulik, if I miss anything, holler out and just keep me on track. So the Green CDT, growing skills for the reliable economic energy for nuclear, funded as part of the CDT call 3-4 years ago for 5 years. We're currently recruiting cohort 4 of 5 cohorts of students. It's a collaboration between the University of Manchester as the lead institution, my own institution, Lancaster University, Maulik's at the University of Liverpool, and University of Leeds, where it's led by Bruce Hanson, and the University of Sheffield, where John Provis is now the lead person for that university. So as I say, it's a from an academic perspective, it's a five university partnership, and Green builds on the success of predecessor CDTs, the Nuclear First CDT, which was exclusively a Manchester Sheffield activity, but then that was followed in 2013 by the formation of the Next Generation Nuclear CDT, and that's when the partnership between the extant 5 universities was cemented. And the mission of Green is, in collaboration with industry, to provide high quality research training in science and engineering underpinning the nuclear technologies, primarily the technology readiness levels of 1 to 3. So this is down below sort of if you like the innovation gap. We are doing fundamental science and engineering, but it is in service more often than not to real problems that are faced by our industrial partners. There was a report generated by one of the skills councils a few years back about the impending crisis in the loss of subject matter experts from all aspects of the nuclear industry. Subject matter expert being essentially nuclear industry jargon for professorial level expertise. And so our mission is to generate the next if you like, next generation of subject matter experts to go into the industry. From 2019 to 2027, the lifetime of this iteration of essentially a nuclear CDT, we're targeting the training of 90 PhD students. We've got 6 million in from EPSRC stroke UKRI. We got 4.1 million from our university partnerships, and we leverage almost another 3 million in terms of university funded students from the partner HEIs. There's 16 industry partners, and that number seems to grow year on year. We're quite accommodating in terms of receiving new industry partners. Historically, the biggest contributors from industry have been Sellafield, Rolls-Royce, the Nuclear Decommissioning Authority, meaning that certainly in the case of Sellafield and the NDA, a lot of the work is focused on the decommissioning agenda, and I'll say a little bit more about that shortly. But the likes of Rolls-Royce and EDF, of course, are very interested in nuclear new build as well. UKAEA, Culham, Tokamak Energy have come on board recently. When we were refunded as green, we spread our wings a little bit from historically being very fission based to starting to include some work relating to nuclear fusion. And over there on the bottom left-hand corner, there's AWE, the Atomic Weapons Establishment, where the majority of the work that we do with AWE is around nuclear forensics and the tracking down of nefarious.
We lost Colin for a bit.
Hello, am I still there?
You're back, Colin. We lost you for a little bit.
Yeah. Okay, but I was just talking about the work we do with AWE, which is around nuclear forensics. It's detecting the bomb makers rather than making bombs. Okay. So here are the areas, the research areas that we're looking at, divided up into three. Current nuclear programs, very heavily focused around the decommissioning agenda. That's probably the area that BEIS historically, certainly over the last 15 years or so, has been very focused on. So that's managing spent nuclear fuel, and managing what are euphemistically referred to as nuclear materials, but which is in fact the 138-ton stockpile of separated plutonium that's currently sitting somewhere up in West Cumbria as we try to figure out what to do with it. Decommissioning and cleanup of nuclear sites as power stations come offline, as Sellafield transitions from being a reprocessing site to essentially a grand cleanup exercise. Sellafield later on this summer will finally close its Magnox reprocessing line, which means that the UK is then officially out of the reprocessing of spent nuclear fuel, and we're then wholeheartedly, certainly as far as Sellafield is concerned, into decommissioning the facilities that are left redundant as a result of that. Geological disposal is a big player, mostly the responsibility of, well, they were radioactive waste management, but they've just rebadged as nuclear waste services, a wholly owned subsidiary of the Nuclear Decommissioning Authority, and they're charged with the siting exercise for the UK's geologic repository, and at the moment is inviting expressions of interest from communities that would like to host the geologic repository. Current nuclear programs also embraces current operating reactors, so that's more effective control mechanisms, it's lifetime extension, and what have you, and nuclear security as well. Again, we're coming back to making sure that this is done safely and securely, and detecting any nefariously secreted nuclear materials. We've got a thread on future nuclear energy, mostly focusing on fusion and what are called future nuclear fuel cycles. So there is a big push on at the moment by the UK government to invest in what are called small modular reactors, essentially reactors that are smaller than the thing that's being built at Hinkley Point at the moment, and orders of magnitude smaller than the thing that's being built at Hinkley Point, but which can be then factory built, thus bringing down the unit cost of a reactor and reducing the financing associated with establishing new power stations, which is the single biggest barrier to the wider use of nuclear energy. So there's a big push from BEIS at the moment on advanced nuclear reactor systems, advanced modular reactor systems, small modular reactor systems, and the idea of cogeneration, using the heat that's generated by bioreactor, not just to generate electricity, but also to drive useful chemical processes such as hydrogen generation, generation of artificial fuels, and use in district heating. And future fuel cycles is all about supporting those reactors in terms of once you've used the fuel in those reactors, what are you going to do with it? Historically, what we used to do is reprocess it. Currently, UK policy is you send it to geological repository, but there's an ongoing activity regarding if the whole world decided to send spent fuel to repository, we would very quickly burn through the uranium supply. So from a sustainability point of view, circular economy point of view, there's a renewed interest in recycling fuel and reprocessing fuel, and it's what that reprocessing system might look like. Certainly the current workhorse reprocessing platform, the Purex platform, if it was to come up for licensing today, it would not get licensed because it is a nuclear weapons proliferation risk. You end up with a separated plutonium stream, and that's just not on. So future reprocessing will all be about harvesting the plutonium that burning uranium in a reactor generates, but harvesting it in a way that means that you cannot use it to make bombs. You can only use it to make fuel for future reactor systems. And finally, we've got a research thread around nuclear energy in a wider context, which embraces such issues as regulation. There's a couple of projects that we've got that are thinking about what the regulation of a fusion-based fuel cycle might look like. Manufacturing, modular manufacturing is going to be a big player for nuclear going forward. Interaction of infrastructure and environment, mostly related to the end of lifetime cleanup of sites, but wider than that. And societal issues, including economic and finance. Finance, as I alluded to earlier on, is one of the big issues that stands in the way of wider adoption of nuclear energy and management of nuclear power. What are the manpower issues that face the industry going forward? The model for green is it's very partnership based. Essentially, a lot of text on this slide, but what it boils down to is how we select projects. And projects can have a genesis either with the academic partners or the industrial partners. The industrial partners might say, okay, we've got an idea for a project here. We're willing to fund half a studentship in this area. Academics then look at those suggested half studentship projects, and if they appeal to them, they can then draw on their reserve of half studentships that each university gets as a result of being a member of Green, match a half studentship to an industry studentship, and Bob's your uncle, you got a full studentship. And the process works the other way around as well. Academics have an idea for a project, they get a half studentship, and they go off to industry and say, okay, got an idea for a project here. Anyone want to match it? Usually they've got a partner in mind, and industry partner provides a half studentship, and again, Bob's your uncle, you've got a full studentship. And then from a strategic point of view, we also fund full studentships as well. Management structure is we have an industrial advisory board. The industrial partners meet once every, usually annually at our winter school. And I'll talk about the winter school in a minute, but more frequently if there are issues that we need to talk around, such as interim review. We have a green management board that meets about every 6 weeks now by conference call. Certainly, the pandemic has formalised the approach that we now use, which is to meet via Teams. We used to meet face to face, but like everyone else over the last 2 years, we've grown to love our Teams meetings. And then finally, we have an oversight of the student experience by essentially a panel of 3 externals, one from Birmingham, one from Strathclyde, one from industry partner NNL, the National Nuclear Laboratory. The structure of the CDT and of the student experience is summarised on this slide. Essentially, we have a core. A core of CDT studentships. These are students that are funded directly by the CDT, either through full studentships or by half and half studentships, universities and industry. But we also welcome non-CDT funded students who are working in nuclear areas. There's a couple of big UKRI funded nuclear consortia out there. There's Transcend, which is focused on decommissioning, 11 university partnership. I think that's eight industry partners. And there's Atlantic as well, which is focused on the reprocessing of future accident-tolerant fuels. All of these have studentships associated with them, but they aren't funded by the CDT. But we're happy to affiliate on a case-by-case basis. We will affiliate students from consortia such as this. The Nuclear Decommissioning Authority runs an annual call for studentships, which it awards 5 or 6 a year out of it, directly out of its research funding portfolio. And we, as many as we can, we try to affiliate those NDA funded students, directly funded students by the NDA. We try to affiliate them with Green as well. So we have a kind of hub and spoke model there. In terms of the structure of the student experience, the first year is essentially a training year, and then years 2, 3, and 4 are when the PhD starts in earnest. The first year is broken down into 3 gobbets. There's a 4-month bespoke talk program. We draw students in from a wide variety of backgrounds. We've had psychology graduates, we've had sociology graduates, mathematicians, physicists, biologists, astronomers. We've had chemists. Chemists are probably the biggest supplier of students to the CDT. Engineering graduates. We take them all in. We put them through a 12-week boot camp. So no specific nuclear background is required. And during this 12-week, they essentially get a view of the whole nuclear fission fuel cycle. It's not just chalk and talk. There's business games, exercises, and case studies are talked about, and there's a strong real-life contribution from our industrial partners. Industrial partners come in and they deliver this boot camp in partnership with the universities. We have site visits we're gifted with a very high density of nuclear sites in the northwest of England. So we take students on, or before the pandemic, we take the students on tours of Sellafield, take the students on tour of the advanced gas cooled reactor over at Isham, just outside of Lancaster here. And we used to take the students on a tour of the Springfields fuel manufacturing facility down to Preston. But that tour at Springfields, which I think is probably the best of the 3 tours, because you actually get to see freshly made uranium fuel pellets almost nose to nose. That tour has yet to be re-established post-pandemic, but certainly we've got coming up in October, we've got trips to Sellafield and to Isham. There's a bunch of public engagement events, and once a year we have our winter school, which is a 3-day residential. This year it was run in York, and due to the Omicron outbreak in January, we postponed that until April. But we are now back to face-to-face winter schools. Usually has more than about 200 attendees, and it's held joint with the Southern Nuclear CDT, the Nuclear Energy's Futures CDT, which is run out of Imperial, but which includes Bristol, Oxford, the Open University, and Bangor. After the 4-month boot camp, the students, which is the boot camp is run out of Manchester as kind of like the hub of a hub and spoke model. The students then return to their home institutions, Lancaster, Liverpool, what have you, and they start a program of student-specific training, two modules. One, SST1, is usually a literature review and report, and then SST2 is where we get the students into the lab or onto the modelling software that they're going to be using throughout their program, and start to get them experienced of the experimental techniques that they'll be following. And that's then followed by 36 months of the PhD research, where they're very much the quality assurance of that then falls very much with the home institution. So in my case, it's Lancaster's quality assurance system will look after Lancaster systems students, Liverpool's system for Morlick students, and so forth. We offer an NGD route. which is where the students can be wholly placed within industry for the period of their PhD. Very few have actually taken us up on that. We also offer a part-time route as well. But again, very few students have taken us up on that as well.
Colin,
in terms of, can
I just say that on that, I think there are students who do internships at the industry also. Like we have one student who's going to Rolls-Royce for the next 3 months to do a small internship over there, and that's also included to the Green CDT.
Yes, I mean that's a good point. Certainly internships are encouraged, and we get offers of internships from the industrial partners, but we also get offers for internships from organisations such as the IAEA, the International Atomic Energy Agency, and the OECD. I can't remember what OECD stands for, but certainly a couple of Lancaster students a couple of years back spent a very enjoyable, well, they told me it was a very enjoyable 3 months in Paris, working with the OECD. In terms of the split of student numbers, it's very heavily skewed towards the technical end of things, but in terms of the current nuclear programs and the future nuclear energy. So what we've got here are the number of students in each area. But nuclear energy in a wider context does seem to be growing. And certainly within the regulation sphere and the societal end of things, there does seem to be a lot of work around the use of digital twins in nuclear. One of the areas where we're disappointed there hasn't been much uptake is in the area of cogeneration, but that's quite new. The idea of using the heat from high temperature nuclear reactors to drive district heating and hydrogen generation and fine chemical production. That's the new one. The chem eng on that has really yet to be bottomed out. So that's an opportunity, I think, for future project work. In terms of EDIA and the COVID impacts, there was, as you can see from the left-hand side, our male-female ratio is something like 60-40. We have a number of non-binary students, but that figure of 60-40, that's a real advance for the industry. The industry at the moment is probably around about 20% women, and it needs a shake-up. So in this context, we regard green and also the Southern CDT as well, the Nuclear Energy Future CDT. We very much regard them as agents for change, agents for positive change, in as much as we really are producing the women subject matter experts of tomorrow. In terms of the home international split, this has obviously been impacted upon by Brexit. We're predominantly home student, although we do have some EU and international students, but rules around EPSRC, UKRI funding do limit how far we can go with that. And in terms of age, we do get up into the senior ranks. We've got roughly about 20% of the CDT is 30 or over, and they're always very very useful to have in some of the sort of like the role-playing exercises, because they bring a certain level of life experience to those exercises that someone who's just fresh out of their first degree can't realise. In terms of COVID impacts, we had to do a certain amount of redesign of the programme to accommodate online teaching. I think cohort 1 just about escaped this. The consequences of the pandemic really only hit early 2020, by which time cohort 1 had gone through the boot camp and gone through the winter school. But the last couple of years have been a struggle. Like most CDTs, we've struggled with this. But we're now happy to say that we have returned to a full face-to-face winter school for the first time this year, as I say, held in York. All of our CDT events were held online in Mozilla hubs. Seminars were held online. The Mozilla hubs things I thought was a great success. It was like a virtual conference. It was as close as you could come to wandering around a conference facility. But nothing beats seeing the whites of people's eyes and meeting them face to face. And what we're hoping is that we are post-pandemic, and that the winter school activity and the face-to-face nature of the assessment of our SST1 and SST2 programs will continue in person for the remainder of the life of this CDT. In terms of the future, or alumni in the future, 70% of Nuclear First and NGN graduates are in nuclear, 90% have gone into technical careers, so there's success there. And in terms of the future, cohort 3 is very much a return to normal delivery of the talk course, the winter school and student seminar events. Cohort 4, we're just starting recruitment there, and we've got the return of site visits to Sellafield and Isham, certainly. We're looking at a refresh of the talk course to include a fusion module because of the inclusion of fusion in the research portfolio for Green. And as well, we've got a series of overseas visits coming up. We've been fighting to get the students out to the CDT students out to a reactor demonstrator facility in Taiwan. Now this has been an ongoing saga for the last couple of years as various COVID travel restrictions ebb and flow in the UK and in Taiwan, but we're optimistic we should be able to do this next year. And I can announce today, and this will be of a special interest to the CDT students that are listening to this online, this is the Green CDT students listening to this online, is that I've been in discussion with the US rep, or the US UK liaison of the US liaison for the UK-US special relationship in nuclear, talking to Andy Worrell yesterday, and we're laying plans now for a tour of US national labs by 20 Green CDT students from the 14th to the 22nd of April next year. So that's just after Easter next year. We'll be off to Idaho National Laboratory, which is the reactor test bed for the US. And we'll be off to the Oak Ridge National Laboratory, which is really the energy research national laboratory in the US, for a week-long tour of those facilities. So there'll be 20 places, and they'll be awarded on a competitive basis. So Green CDT students, if you fancy a trip to the US just after Easter next year, then I encourage you to start working on your CVs. And of course, like every CDT that's funded by UKRI, we face interim review. We're thinking about that at the moment. And that's it, really. That's the overview. Moloch, have I missed anything?
No, I think everything's covered, Colin.
In which case, I'll hand back to. I'll take any questions. Hand back to Mark in terms of control of this.
Thank you, Colin. Okay, so to start with, we're going to have Charlie. Charlie's going to go first, which is a change to the agenda if anybody's looking at said agenda. Hold on a second. Okay, can everybody see that?
Yes.
Okay, yes. Awesome. Okay, go ahead, Charlie.
Can I control this from here?
No, I think I have to. So I think you'll have to do some hand waving to me to go forward.
Okay, never mind. And the font's
it's only
wrong.
3 slides.
That's true.
How much can I screw that up?
The font's wrong again. Okay. So, hi everyone, I am Charlotte Maria Stintz. I have an MChem from the University of Manchester. My pronouns are she and her. And my PhD project is Mechanisms of Radionuclide Retention in Aged Cements. Click on for me, Mark. There we go. So I am a mature-ish student. I form one of the senior ranks, as was subtly said by Colin. And I did my master's project here in Manchester, and it was purely synthetic chemistry, heteroallyl activation by FLP phosphorus zintal clusters with the meta group. And again. No, the other way.
Yeah.
There we go. Outside of uni, I support my partner who runs an LGBTQIA organization called Forward in Stockport. Together, we both absolutely love traveling. We did a big tour around Europe last summer, and I'm eyeballing both Taiwan and America very, very excitedly. And one more. Other way. And in my spare time, I volunteer on the East Lancs Railway and I clean and fire steam engines because, you know, that's what I do. All right, let's get on with the project. So if you can jump forward again for me. Okay, so now a few things have changed since I actually wrote this presentation, but most of this is still pretty good. So there's 3 sections to my project. The first one is we need to figure out what the aged cement materials are going to look like. And so that involves figuring out what cement phases are going to be present in the GDF in about a timescale of about 10,000 years. There is quite a bit of work that's already been done on this, but this part is about pulling some of that together. Something else I've already made a start on, I've started looking into the actual mechanisms of radionuclide uptake. This is starting using some NNL material, which I'll get to in a second. And then finally, the last part, which we haven't really kind of started on yet, is exactly sort of what's the fate of these radionuclides. So this is going to be artificial aging of the cements with those radionuclides present. And again, please, Mark.
Oh.
Try again. Click again.
Oh, there we are. Is that it?
Yep. And okay, so first part, there were 4 sort of key areas of research in this. I was looking at some work done by Hoch et al. Back in 2012. This is a complete setup of modeling of a GDF. This tended to be focused a lot on the pH present in the NRVB material and the backfill material. We're also looking at the natural analog site in Jordan, so reviewing some literature around there. Again, getting a feel for the cement phases that are going to be present. We've got a collaboration going on with Imperial College. Doctors Wong and Myers have their PhD student, Tom Budd, and they're working on creating, or they've actually created a model, or a model of how I had this practiced a while ago and now I don't have it in my head. They're working on creating a computerized model of exactly what cement phases will find given specific starting materials, conditions, and a time frame. And they are currently developing, they're actually currently running this model for us. And then finally, I have got some samples from NNL, which they very kindly provided me of aged cement samples. So moving forward into the next part, there is going to be some batch testing of radionuclides onto different cement samples and cement phases. I've already started this with the NNL cement. It says down there in the 3rd line where I've sorbed uranium-6 onto NNL aged and the fresh NRVB, and we were in Diamond last week at the synchrotron, and so I'm currently processing those data. But there's going to be a selection of different materials, different radionuclides, which we're going to try sorbing onto the cement, and it's really about understanding that speciation in the artificial environment. Last one for me, Mark. And then the third part is about varying the cement portfolio. And like I said before on the previous slide, this hydrothermal aging of fresh cement samples with the radionuclides present to understand exactly how they change and what their behavior is as the aging process goes on, because obviously they're going to be underground for a very, very long period of time. And then the final goal is to really be able to put together a picture of what it's going to look like over the entire lifespan of the GDF, or at the very least up to about 10,000 years. And the next slide should be the closing slide. And so it is. That's me done. Thank you very much.
Thank you, Charlie. Okay. So next we have Federico. Is Federico here?
Yes, I'm here. Can you hear me?
Okay. Yep.
Okay.
Can you see the screen? Is your presentation up?
No.
Oh no. Try.
Yes,
Okay. How about that?
Yes, perfect.
Okay, Federico, are you ready?
Yes. Okay, so good afternoon, everyone. My name is Federico Bellatini. I am a nuclear engineer who graduated from the University La Sapienza in Rome. And during my academic career, I soon realized that my interest falls mainly in thermal hydraulic applications. So I expanded my interest with a thermal-related master thesis, and now I would like to develop know-how on the fluid dynamics side. And this is why I decided to do an experimental fluid dynamics PhD at the University of Liverpool, which will be supervised by Dr. David Dennis from UOL and Dr. Jonathan Dodds from NNL. My project will focus on the development of flow and settling correlations for the transport of nuclear slurries in partially filled pipes. Next slide, please.
I think, Mark, we cannot see the slideshow, at least. I cannot see the slideshow.
Oh, you can't. Oh,
no.
It's the slides only that we can see.
Okay. Let me try again.
Good. Yeah.
Okay, perfect. Yeah, it's the one before. The slide before, Mark, please. Okay,
yeah.
Thank you. So as you may already know, a slurry is a mixture of tiny solid particles suspended in a liquid. In the nuclear industry, slurries are used mainly for waste transport, and the understanding of their flow is crucial for an efficient clean-out and decommissioning of pipelines within nuclear facilities. There are three main problems with slurries. Firstly, they are two-phase and non-Newtonian fluids, which means they do not follow the traditional flow laws and correlations. Secondly, nuclear slurries are often transported in partially filled pipelines, which have both features of a full pipe and an open channel flow. But unlike the latter, the literature remains underdeveloped, with work often limited to studies of water. And lastly, because of the suspended particles, the risk of sedimentation is quite high, and this can lead to pipe blockages, which are potentially disruptive and costly. So the goal of my PhD is to answer these three challenges by gaining a greater understanding of the flow, by predicting the transport behavior, and developing and validating flow correlations. Next slide, please. Okay, so far.
Sorry about that. There you are.
Worries. So far, there is some research on Newtonian fluids flowing in partially filled pipes, and there are very few, if none, works of non-Newtonian fluids in partially filled pipes. We would like to fill this gap with a project organized in three main phases. The first phase will consist of experiments conducted at the very large scale pipe flow facility at the University of Liverpool, where different model polymeric solutions, such as carbon xanthan will be used to imitate the properties of slurries. And the experiments will be conducted in a pressure-driven scenario, which fully turbulent Reynolds numbers and with field height ranging from 30% to 80% of the pipe cross-section. The second phase will consist of experiment at the slurry transport rig at the NNL Workington facility. The STR will be used to measure the flow rate and field height in a gravity-driven scenario over a wider range of turbulent Reynolds. And in this second phase, we plan to investigate also on the settling using chalk as solid in suspension. And finally, the results from the results of the work from phase 1 and phase 2 will be used to produce transport correlation to describe the flow and the settling behavior. Yeah, that is everything. Thank you very much for your attention.
Thank you, Federico. Okay. Next up, we have Anaya. Are you here, Anaya?
Hello, Mark. Yes, I am.
Okay. Well, let's have, hopefully we'll have a better luck getting your presentation up. Can
I share my presentation because there are lots of animation effects?
Okay. Yeah. Let me see what I can do.
If I can share from my side.
Yep.
Okay, just a minute. Is it visible?
Yep, I'm seeing that.
Okay, so hello everyone. My name is Ananya and I am from India and basically from Varanasi. Varanasi is an old and beautiful city on the bank of river Ganga. So I have done my graduation from Banaras Hindu University in geology honors and then went to IIT Bombay for my post-graduation in applied geology. I like painting mandala art and rock collecting, and I have learned music and dance. So about my project here in University of Manchester, I'm doing my research on the topic, the impact of microbial metabolism on cement properties during radioactive waste disposal. My main supervisor is Professor John Lloyd and co-supervisors are Professor Dirk, Professor Kat and Professor Sam. So what I am doing. There are three objectives of my project. The first one is to monitor the extent of the impact of microbial metabolism on cement in a long-run experiments in some GDF relevant conditions. And then we will try to get some XCT and 2D, 3D SEM imaging on those samples to monitor any in situ changes. These data will be generated for EU MAGIC project for further modeling. So why this is important? You all know that nuclear fuel cycle produce a lot of radioactive waste material and GDF is emerging as a solution for deep underground burial of these waste. GDF is a multi-barrier system in which cement is used as backfill and for constructions for low-level waste and high-level waste facilities. Recent study shows that there is a possibility of microbial growth even in the harsh condition of GDF, and microbial metabolism can have a positive as well as negative impact on the cement material. So it can have a biologically induced corrosion effect on the cement as shown in this figure, or microbiologically induced carbonate precipitation can be helpful in filling the cracks in long run as shown in this figure. So it makes it important to study the microbial growth and its impact on the cement system and its composition, which can affect the integrity of the GDF. So that's it.
Thank you.
Questions?
Okay. So next up we have Edwin. Edwin, are you here? Oh no, I think Edwin's not here. So Corinne? Get yours up.
Hiya.
Hi, Corinne.
Mark, we are still on Ananya's presentation slides.
Oh, right. Request control. Okay, is yours up now?
Yeah, that one's mine.
All right. So thank you, Malik, for your critique in the background. Helped a lot.
So hi, I'm Corinne. I'm working with the Green CDT at the University of Manchester, and I'm working with Professor Kaltsoyanis and Dr. Natrajan, and I'm currently in the lab at the moment, which is currently why there's so much background noise. I'm currently looking into building a comprehensive view of the redox reactions that occur between uranium and iron-bearing minerals using computational and experimental techniques. So a little bit about me. I did my MChem at the University of Manchester, and I did my fourth-year project looking into computational modelling of copper-1 complexes for photosensitizers. And I like to row in my free time, and this is a picture of me at Women's Head of the River in London in about March, where I technically raced against the Olympic gold medal winning women's Olympic Rio and London 8. Let's just say it didn't go very well. Anyway, next slide. So a little bit about the background behind my project. I'm sure we've all heard it loads of times before. So currently uranium and other high-level waste is currently being stored in short-term storage pools in Sellafield, as you can see on the left-hand side. This is not a long-term solution as it requires constant maintenance. With a half-life of 700 million years for uranium, this isn't a long-term feasible solution. So what the UK government and other governments around the world is they're looking into into making geological disposal facilities, also known as GDFs, and this is shown on the right-hand side. So the entire idea behind a GDF is that there's multiple barriers which then prevent the release of radioactive nuclides into the environment because of their long-term effects on the environment. But also it protects the high-level and intermediate waste from the environment. For instance, uranyl is extremely mobile in water, and thus we need to limit its mobility. So my research is looking into the rock layer of the GDF, which is the final barrier. What we're looking for is a mineral that is very abundant in the UK, but also depending on the conditions of the GDF that we can build into its design, will also incorporate or absorb uranyl and other radioactive nuclides very easily. So next slide, please. So how am I going to do this? Well, I'm going to be doing this via DFT, which is density functional theory, and this is shown on the left-hand side. This is done using a model within that called the periodic electrostatically embedded cluster model, also known as PCM. And currently I've been modeling the interactions between uranyl and goethite and reduced uranyl and goethite, and how this changes the bond lengths, the geometry, the absorption energy. Computational chemistry is very useful for gaining a lot of information on a particular species once the model is built. However, often building the model can be a big problem, and we need to work alongside, we need experimental results to ensure that we've built a correct model. And this is where the experimental techniques are coming into this. So this is shown on the right-hand side, and various spectroscopic techniques will be used, such as emission and excitation spectroscopy, Raman, and batch sorption to determine concentrations of absorbed uranyl onto various minerals. We're thinking that we're going to be looking into hematite, as a lot of work has previously been done on goethite. Thanks for listening.
Thanks. Okay, is Tom here? No, Tom. Okay, Sam.
Hi, Mark.
Oh, you're here. Excellent. Right, let me give you the screen. Okay, can you is your presentation up?
Yes, there are lots of animations, so you'll have to keep on clicking.
Okay, yeah, that's fine.
Hi everyone, I'm Sam from University of Leeds. My research topic is on licensing small modular reactor in the UK under the supervision of Dr. Tristano Sainati and Professor Bruce Hanson. Small modular reactor is a low carbon energy source. It is small as it has a footprint of 2 football pitches, but it can power around 1 million houses, which is the equivalent of the Leeds city. Next, it is modular, that is, it is manufactured in the factory, transported as modules, and installed on site as and when in demand. Next, the reactors have an electric power output between 10 megawatt to 300 megawatt. Next, in the UK context, we have the Rolls-Royce SMR project, which is ongoing. There is a strong belief that this technology will play an important role in the decarbonization when deployed in 2030. You'll have to keep on clicking, Mark.
Yep.
Yeah. It has strong support from the government and the private sector. But in parallel, we also notice that a significant sum of money is being invested in the development of regulatory frameworks for the SMRs. Let's have a look why. Yes, you have to click. Yep. The SMRs, being a first of a kind, has many novel approaches in its design, safety system, and deployment scenarios. In theory, this is very meaningful and exciting, but in practice, it is very difficult to deploy under the prevailing licensing conditions. This is mainly because the existing licensing processes has been operated and designed on large reactors. As such, they are not fully compatible with the envisaged benefits of SMRs. You'll have to go back.
Oh, sorry.
Yep.
What happened there?
Yep, that's good. Yeah. So yeah, they are not fully compatible with the benefits of SMRs, leading to longer licensing duration, expensive licensing costs, and thus higher investment risk. My research objectives would be to identify the barriers affecting the deployment of small modular reactors in the existing licensing process, and then to identify the potential solutions to overcome those barriers without compromising safety. My plans throughout my PhD is to build an interdisciplinary project through expertise from different knowledge, such as engineering, project management, economics and finance, and legal. I also intend to engage with different stakeholders through conferences, training programs, internships, and research methodologies to collect data. Eventually, I aim to come up with solutions to overcome the barriers affecting the SMR deployment. Thank you for your attention.
Thanks, Sam.
No worries.
Charlie, Charlie Nevin, are you here? Awesome.
Hello, can you see me and hear me?
I can hear you. Can you see the slides?
No, that could just be me though. The internet's a bit dodgy.
Okay, hold on a second. Okay. How about now?
Yeah, if you just make
Awesome.
it full screen.
Awesome.
if you just do the slides.
Oh, it's not full screen for you?
No, it's just like the PowerPoint.
Sorry about that.
Perfect.
Okay.
Thanks, Mark. Okay, so hello, I'm Charlie, and I'm a graduate from the University of Sheffield. I graduated in 2021 with a master's in chemical engineering. So I'm continuing on in the same department with Dr. Brant Walkley and Professor John Provis, looking into resolving reaction. Oh, what was written on the slide? Resolving reaction mechanisms, kinetics, and mass transport in radionuclide loaded geopolymer cement waste forms. Next slide, please. So why do we need to tackle the issue of waste? So as you all probably know, in the UK alone, over 150,000 tonnes of radioactive waste has been produced to date. So this is enough to fill approximately 60 Olympic-sized swimming pools. So lots of this waste is obviously radioactive, so it makes it extremely difficult to handle, and it needs conditioning to prevent its release to the biosphere, where it can harm us and animals and plants. So one of the methods to prevent this release is through encapsulation in cement. So I'm looking into a novel cement for this application called a geopolymer cement, and they are attractive compared with traditional Portland cements, as they can stabilize nuclear waste at lower temperatures. They have a higher fluidity of preparation. They have high chemical resistance in aggressive environments and high chemical tolerance to problematic wastes. They have enhanced capture of radioactive waste compared with Portland cement, and lower leach rates, so less of the radionuclides are going to get out into the environment. And finally, they produce less CO2 per tonne than Portland cement. Next slide, please. So my project aims to provide a greater understanding of geopolymer reaction setting and hardening, along with investigating the mobility of fission products and the waste retention. So my project's changed a little bit since I've made this presentation, but it's mainly still right. So if you click again, oh, other way. Yeah, there you go. Oh, you can see it there, but
Sorry.
no, that's okay. One more time. There, oh, there we go. So my project focuses mainly on the last two of these points now. So I'm still going to do some of the characterization of the formation, but a colleague of mine is doing most of that. So I'm doing mainly the determining the radionuclide cement interactions and assessing radionuclide retention in repository relevant conditions. So these conditions are UK synthetic groundwaters, specifically granitic groundwaters, because that's what the rock is around lots of Cumbria where our GDF might be sited, and GDF temperatures, which can range between about 20 and 90 degrees C. So yeah, thank you very much for listening.
That's Charlie. Okay, Jess, is Jess here? No, I don't think. Oh, yes, you are. There you are.
I am, and I've just spilled just in myself. Awesome.
Oh, no.
So I'm going to pre-warn if I've had 2 cups of coffee, so if I start going really Scottish, I'll get some subtitles going.
Okay. Tell me if we look good.
Yeah, if you can go one slide back, please.
Oh, that's
Thank
weird.
you. I mean, it's really just for the dog. The dog is to distract
Yes.
any sort of questions. So, hi, I'm Jess. My PhD is on geopolymer cement for the mobilisation of radioactive liquid organic wastes. Massive mouthful. Don't worry if you don't know what half it means. I don't either. I'm doing this at Sheffield University under the watch of eye of John Provis. I'm co-funded by EU Prius. Before I came to Sheffield University, I did my undergrad at Strathclyde in Glasgow, and I did this in a master's in chemistry with forensics and analytical chemistry. So slightly different from cement, but you can put a dead body in it, so it kind of works. Next slide, please. So my project focuses on two organic waste oils known as TBP and nevastane. TBP is known as no. Did my Wi-Fi drop?
Yeah, you froze in mid-sentence.
That's okay. I think my computer sensed fear and went, nah, we're not doing this today. We'll try again tomorrow. Cool. Sorry. So TBP is used in the nuclear cycle, and the whole point of it is to process uranium so we can kind of recycle it and reuse it, because obviously it's not an infinite source. It is finite and will get used up at some point. Nevastane is more to represent general oil waste that is produced throughout the nuclear process, such in manufacturing and lubrication. Both of these are known as secondary wastes because they aren't directly produced by the nuclear process, but are instead byproducts. And they are both known as problematic waste streams because there's actually not much of a solution yet for them. My focus is geopolymers. Why should we use geopolymers and not Portland cement? Because Portland cement is actually great. It's used for encapsulation of low-level and intermediate waste. Slight problem though, when you put oils in the Portland cement, it tends to retard the hydration process, so the cement doesn't set, which not the best thing if you have a radioactive material inside of it. Oh, okay, we're just going between all my slides now, are we? Geopolymers can. So geopolymers don't do a hydration process. They do a polycondensation reaction. So simply means they'll set. Next slide, please. Maybe. Thank you. So the current plan is a bit all over the place. The first part was to research this topic, which I'm going to be honest, I like to believe I've done to death. This will be produced in the results of my SST1 and SST2 report that I will hand in at some point. A really good paper that covers this topic, if you're super dead interested, is in the QR code below. Don't worry, you don't actually need to scan it. I get that I'm the only one interested in this topic. Next is to develop a kind of strategy. I've been given samples from NNL Workington that are geopolymers with both types of oil in it at different percentages and different conditions. I've been tasked to do analytical techniques on both of them in the form of SEM, FTIR, NMR, and XRD. The whole point of this is I can try and work out how the oil sits in the cement, and working a bit backwards, I'm going to then go back and make my own samples, which I'm slowly getting around to once everything clears customs, and validate my own samples. Thanks for listening. I hope it's gave you a bit of an insight into my PhD.
Thanks, Jess. Okay, Ashley, have we got Ashley here today? I don't think Ashley's here. Jack?
2 seconds.
Oh, are you here? Ashley?
Hello?
Hello, Ashley.
Hi, can you hear me?
Yes. Okay.
Sorry, I was just looking for a quiet room. My office just got really busy.
Oh, no.
Okay.
Bad timing. Can you see the screen?
Are you sharing my slides?
Yeah, I was. Are you there, Ashley?
Yes, I'm here. Can you not see me?
I can.
Can you see the slides, Ashley? No?
No.
Oh, for crying out loud. Better? Can you see now? No?
It's one of your folders, Mark. It's the.
Oh. Hold on.
Oh, yes. I can
That's
see
it. Okay.
Yeah.
Oh, there we are.
Okay. Hello, everyone. I am Ashley, and I am doing my first year here at the University of Leeds. I am working with Professor Timothy Hunter, and my supervisor is from Sellafield, Martin Barnes. So I graduated 2021 from the University of Rochester with a BS in chemical engineering. Over there, I did a lot of work looking into wastewater treatments. So all the garbage from your homes, it goes onto this garbage management site. So that picture there is just me getting a lot of that liquefied waste from the underground. You can imagine the smell of that, but it was fun projects like that, looking to purify that. So quite a bit of waste management, and then a lot of computational modeling with the University of Reading. So looking to study piezoelectric effects in the bone. So that's quite a bit of Python, MATLAB. So a combination of like waste treatment and the computational side of that brought me to this project, which is bubble growth and gaseous release dynamics within viscoelastic waste sediments. It's quite a mouthful, but basically it's just looking at bubbles and gas held up in the waste stuff that they have over at Sellafield. Next slide, please. So we all know that Sellafield has quite a few waste management plants on site. So one of them is handling the first generation Magnus-Swaff silos, which is all the stuff that's in the ponds. And they also have 6-SAP, and 6-SAP is basically like, it's like the kidneys of Sellafield. It just takes all the stuff from the different waste management plants and it filters it through before it's going into the sea. So they want to take out stuff like cesium, strontium, and a lot of these waste sites, they have the ponds, for example, you have these skips that are immersed in the water. So they are really concerned with, obviously, now that Sellafield is closing up reprocessing, starting up decommissioning, when they start moving the skips around, they don't know how much hydrogen is trapped in those sediments. So they know how much is being released. They can measure that, but they don't know how much is trapped in all these different sites. So my project, that's the nuclear kind of motivation for my project. Next slide, please. In terms of the actual scope, so there's a lot of people who've done a lot of work looking into how hydrogen is formed and how bubbles are transferred in sediments. I'm kind of coming in back to the basics. I'm very much looking at the fundamentals of this. So how does a bubble form, the shape, the size, obviously the kinetics of all the different sediments. So the types of beds they have at Sellafield, sort of like ion exchange beds in the ponds, those types of sediments are obviously very complicated. They have quite a lot of different radioactive stuff going on in there. I'm not doing anything quite that complex. I'm just going to be scaling it down. So maybe just looking at like glass spheres in a column and then seeing how that works with bubbles. So it's really simplified. It's back to the basics. As you can see here on this image, you can just put like hydrogen peroxide with water. You get those bubbles forming, and then you can study how much gas is being released against how much is being trapped over time. So these experiments, currently I'm running them for like 5 to 10 hours to study the gas. Obviously, looking at Sellafield, they have this stuff for like decades. So experimentally, you could argue that it's not going to be quite the same, but we're also putting it together with stuff like X-ray tomography and some computational modeling to be able to see what happens over time, over long time scales. So, yep, that's me.
Thanks, Ashley. Okay, Jack, are you here, Jack?
I am. Hello.
Okay, let's see. We have. Okay, is your presentation up?
No. No.
Hold on.
Oh, nearly. Oh.
Okay. Okay, now?
No, not yet. Still.
Oh. Now?
Nah, still not up. Do you want me to share it?
Yeah, yeah.
Right, okay. Well, I've got to find it myself now. Sorry, I can't find it on my computer.
Okay, let me try it again.
Yeah, that's all right.
Is that it?
No, still not yet. It's just coming up with all the files on it on your yeah, all the files.
Okay, maybe I've got to.
Oh, I found mine. Right, tell you what, I'll just present on it, yeah. Can you see my screen now?
Nope. Hold on a second.
Right, okay.
Right. Is that it?
Hey, there we go, yeah.
Right. Okay.
Right. Let's go. Right, okay, so yeah, my name's Jack, and I'm doing a PhD in disposal mocks here at Lancaster University. A little bit of background about myself is, well, essentially I did my undergrad here as well. I did it in chemical engineering, and after doing my dissertation on predicting fission product inventories in MOX fuel, decided to carry on because I enjoyed it, and here we are now. So yeah, if you mind pressing next slide, please. So a little bit of background about my project, like what's already been mentioned by some other people before. We all know that the UK's got quite a substantial inventory of spent plutonium, which has kind of come about from its long history of running a closed fuel cycle where we've been recycling the fuel. So we've got the largest civil stockpile in the world of around 140 tons, and it's preferred that the size of this stockpile is reduced. So there's quite a few ways of doing this. You can either turn it into MOX fuel and put it in a thermal reactor, or immobilize it in in some kind of immobilized product and then send it off to direct disposal in a GDF. So the option preferred currently by the UK government, which was decided in 2011, was that we were going to put it all into MOX fuel, and any part that was unsuitable would be immobilized and directly disposed. Because what's ended up happening is through the storage of like this plutonium, some of the plutonium has become contaminated due to the radiolytic degradation of PVC, which was used as like packing material. So this plutonium has been contaminated with chlorine and it's not suitable for use in MOX fuel. And it should also be kind of noted that that's currently the government's strategy, to build MOX fuel, and what's not unsuitable gets disposed. This could change due to the current strategy being like unviable or uneconomical, which would then mean that the entire country's inventory would need immobilizing and directly disposal. So there's quite a few potential ways that are being examined by the NDMA to create this disposal product. And one, which is the focus of my PhD, is disposal MOX. So can I have the next slide, please? So that brings us to like the aims and objectives of my PhD. So I'm going to use plutonium simulants, mainly cerium oxide, to kind of optimize the formation of some disposal MOX pellets. So I'm going to be using conventional sintering methods, such as cold press and sintering, and also going to be experimenting with new rapid sintering methods, such as spark plasma sintering and flash sintering. which could potentially lead to a denser product, because obviously the denser the product, the more plutonium I can get in, which makes it more optimal for direct disposal. I'm also going to explore both heterogeneous and homogeneous routes. So heterogeneous is like the direct blending of the uranium and plutonium powders, well, cerium in my case, sorry, to form the product. And homogeneous will be like, for example, following like the oxalate route, which would make a more homogeneous product, which could potentially lead to getting a higher plutonium load in. So I'm also going to be putting some neutron poisons into the pellets to avoid criticality, such as hafnium and gadolinium. So I'm going to be trying to understand how the amount of these can affect the quality of the pellet. So can I have the next slide, please, as well? And then once I've done that and I've created a series of disposable MOX pellets, I'm going to assess their disposability, which is going to be using electrochemistry to understand their corrosion behavior conditions relevant to those that will be found where they end up, which will be in a... Oh,
sorry.
It's all right. It's all right. I'll just carry on chatting. Yeah, the conditions that will be relevant to those found in a GDF. So that is going to be both the pre and post closure conditions, so in oxic and anoxic conditions, and yeah, basically seeing how these pellets hold up in a GDF, yeah, that's kind of everything. Thank you.
Thanks, Jack. Abby, are you there? See you there, Abby?
Yeah, I'm here.
Okay, awesome. Let me screen with you, Abby, and are we?
Yeah, that's it. Perfect.
That's it. Yep.
Right. Okay. Hi everyone, I'm Abby, and my PhD is on improving the understanding of gadolinium for use in neutron detectors. And I'm working with John Coleman, Yanji Schnellbach, and Stephen Quillen from AWA. I'm based at the University of Liverpool in the physics department. I also did my undergrad there, which was integrated masters in theoretical physics. I'm also from Liverpool, which is probably obvious from the accent by now. So another few years in Liverpool for me. But about my PhD project. Oh, could you next slide, please, Mark?
Yep.
Thank you. So this is just a quick motivation slide about the project. So in particular, we're interested in 157 and 155 gadolinium, as they have really high neutron capture cross sections. And upon capture of a neutron, they produce a cascade of around 4 gamma rays. You can see the decay equations there about how that goes through. The energy released in these reactions is about 8 mega electron volts, which is really high for a nuclear event, which is why we're interested in it. The table on the right shows the cross sections of these isotopes. Could you just click for me, Mark?
Oops.
Oh, sorry. Yeah, that one, that's fine. Quite small to see, but 155 has a cross section of about 60,000 bonds and 157 has 254,000, so that's really high. However, the model for this decay, when it captures the neutron and produces this cascade, is not well understood, so that's what we want to work on here. So we hope that improving this understanding will then lead to better neutron detection via event identification and background discrimination. Next slide, please. Yeah, that one. Thank you. And this is how we're going to go about doing it. So overview of methods. We'll be using a mixture of computational Monte Carlo methods, as well as hopefully some experimental methods. So starting on the computational side, we want to be using Geopolymers models, which is a simulation toolkit, which models the movement of particles through matter. And we'll also be using a Monte Carlo code package called Dicebox. This already exists for gadolinium, but we're hoping to improve on this as we go through our research with the decay mechanism of gadolinium. There has been some recent research, quite similar to what we're proposing at JPark a few years ago. The spectra on the right shows their results from gadolinium thermal neutron capture. We want to do our own experiment, but with improvements, hopefully at the Institut La Langevin in France, and hopefully improve on these findings. Once we've done that, the experiment, assuming we get approved on the proposal, we can then combine this with our computational methods and hopefully achieve a good model for the gadolinium mechanism of thermal neutron capture, which can then be implemented into multiple different types of detectors. And that's all from me. So thank you very much for listening.
That's Abby. Louisa, are you here?
Hiya, yeah.
Oh, awesome. Hold on a second.
Hi. Yeah, sorry, the lighting is really bad in my flat. But, yeah.
Right. Right. Okay, is it up on the screen now?
Yeah, it's perfect.
Okay, great.
Okay. So hi, my name's Louisa and my project is called the Transport of Radioactive Waste Along the Sellafield Shoreline, Climate Change Impacts and Mitigation Strategies Through Nature-Based Solutions. It's based at the University of Liverpool and I'm being funded by NNL. I have a bachelor's degree in environmental science and a master's in nuclear, which go very well in working on this project. Can you go to the next slide, please? So a bit of background for this project. Sellafield is an extremely complex site that has had a lot of different processes have gone on the site, and that has led to a lot of different types of wastes and radionuclides that have found their way into the environment. There's been, well, three main sources, actually. It says two, but there's three main sources of pollution from the site, which is authorized discharge into pipelines that have gone into the Irish Sea. There has been leaks, and now there is remobilization of legacy waste that has been collected in the bottom of the Irish Sea in the sediments. And the radionuclides can be found, again, as I said, in the Irish Sea and along the mudflats inside the Irish Sea on the seabed. So understanding how these radionuclides move in the environment will aid remediation efforts in the future. Can you go to the next slide, please? So I will be using a coastal modelling software called Delft 3D, which will look at the hydrodynamic effects of radionuclide remobilization. So that's seeing how the sort of the wave patterns from rivers and sediment movement will affect the remobilization of both sediments that are contaminated with radionuclides as well as radionuclides in the aquatic phase. So we'll also be looking at the effects of sea level rise and future climate change, mainly because sea level rise is a consequence of climate change. So it is the factor of climate change which will mostly affect my project. And the effectiveness of nature-based solutions will also be modelled. So that's looking at things like reed beds, which as they grow will bioaccumulate the radionuclides into the tissue of the plant. From there, they can be removed and disposed of as radioactive waste, thus removing the radionuclides from the environment. We'll also be deducing the effect of radionuclide pollution on the environment and trying to look at mitigation strategies, which will hopefully be fed into legislation and fed into the industry as well. Thank you.
Let's do is yeah. Okay, Aaron. Yep, I see you're here, Aaron.
Hello.
Okay. Are you up on the screen there? Can you see your?
I cannot see a presentation.
Okay. Is that up now? Okay.
Not as far as I can see.
No.
I do have it, so I can share it if that's easier.
Okay. Do you want to do that?
Okey-dokey. Is that working?
Ah, yes, just come up.
Right, good. So hello, I'm Aaron. Can you see that okay?
It's gone again.
Oh, right, okay. That was when I tried. I'll do it without the full screen, if that maybe we'll keep it up there. But yes, my name's Aaron, and I'm looking at the development of novel sample preparation techniques for the analysis of microgram quantities.
Still nothing up. Do you want me to let me try again?
Yeah, you have another go.
Oh, that's the wrong one. Is that it?
Yes.
Yeah. Okay, great.
Okay, right. I'll try again then. So yes, my project is looking at the development of novel sample preparation techniques for the analysis of microgram quantities of bulk actinides. So initially, about me, I did my undergraduate degree at Kiel University in physics and spent a year in Sweden at Uppsala University, and found that I enjoyed sort of nuclear physics and radiation, and sort of particularly enjoyed really the practical applications of the theory that was being taught. So in terms of the project, I suppose breaking it down a bit, it's looking at the feasibility of reducing the sample size of actinide materials like uranium and plutonium, and seeing whether or not you can sort of keep the same amount of information. So taking it from maybe grams or tenths of grams down to micrograms. So why would you want to do that? Well, there's sort of two main reasons really, and the first one's the most important, which is to improve the safety. The smaller the amount of active material you're handling, the less radiation it's going to be emitting, and also when doing sort of risk assessments and things, you take usually the most extreme case. It's very conservative, so you would look at, accidentally ingesting the entire sample or something if an accident were to occur, and so the smaller sort of total size of your sample, the less dangerous it is. So the second kind of major reason is to reduce waste. So some analysis techniques are destructive, meaning that you lose that sample once you've used it, or it may require a preparation technique, for example, dissolution into acid or being milled into powder, and it might not be usable to you after that. So obviously the less that you're wasting, the better. It's also very expensive to dispose of waste. So in general, really, any kind of lab or maybe manufacturing facility which is using active samples could be helped. Obviously, it's expensive, so you don't want to be you sort of want to be keeping as much of your original material around as you can. And you also may only start off with a small amount. So a lot of these materials are quite tightly controlled, so you may only be allowed to have a couple of grams sort of on the premises. And in, for example, nuclear forensics, you may only start off with sort of a trace amount of material that you're kind of looking to see. You're trying to get as much as possible out of it. So next slide, please. So how? Well, the first step is to look at the sample preparation techniques. So the main one really is focused ion beam scanning electron microscope and laser cutting, and that will be used to cut very, very small lamellar samples. and then they will be analysed using different mass spectrometry and surface techniques. So I've got a few there, but there are the pages and pages of different acronyms that you can use to test it. And these results will then be compared with sort of bulk radiochemical techniques which have been performed on maybe the parent sample, so what is currently being used. And you can look at the two and see whether or not you lose any sort of important information, or you sort of lose the big picture by reducing the sample size. And then kind of another one of the goals really is to look and see if there is a minimum sample size or a point at which the reduction in the sort of the sample size that you're using, you know, the benefits no longer outweigh the sort of the reduction in the information that you get from it. So that's all. Thank you.
Thanks, Aaron. Okay, William, are you here? Okay, Jonathan.
Hello.
Okay, Jonathan, let me get your project up.
Can you hear me okay? Is the microphone
Yeah, it's not great, but okay.
Probably the Wi-Fi. Just let me know if I drop out.
Is your project up? Excellent.
Yeah, brilliant.
Oh,
okay.
well, I knew we'd get there in the end.
Okay, right. Hello, everybody. My name's Jonathan. A bit of background on myself. I graduated from the University of Aberdeen in 2017 with a Master's of Chemistry, and I've spent several years in the hazardous waste industry in offshore oilfield waste before coming to Manchester to do this PhD. So my PhD is in the area of nuclear decommissioning and land quality, and it's on the concrete sediment interface funded by the NDA. My supervisors here at Manchester are Professors Catherine Morris and Sam Shaw, and Dr. Victoria Coker, and James Graham as my industrial supervisor. So just quickly, the picture on the left there is the Sellafield nuclear site, which is kind of the focus of my research. And if you just take a look at it there, you can see there's a lot of concrete there. So great. Okay, next slide, please, Mark. Okay. So the environment around concrete structures is complex, and it's relevant to a number of scenarios. This research is going to focus on near subsurface, so I'm not really interested in the geological disposal side of things, but you can have scenarios around foundations of buildings where contaminant plumes are being moved through the groundwater, or primarily we're interested in situ disposal scenarios, some of which are illustrated on the right-hand side there. This is essentially dealing with material from demolished buildings on site, on the site, rather than transporting them to specialized disposal locations. Primarily, this is for the lower levels of contaminated materials, so things like foundations and building materials like that. There's going to be several hundred thousands or millions of cubic meters of this material, and you can imagine at £10,000 per ton, that's going to add up to billions fairly quickly. So any savings we can make here would be fantastic for the industry. Initially, we're going to focus on strontium 90, and then move on to some other contaminants that have been identified as priority radionuclide contaminants at Sellafield, such as technetium 99 and actinides like uranium. We're interested in what happens when these materials are carried to the cement, and then how stable they are in that scenario. So are they going to be leached away by groundwater or seawater ingress from seawater rise? And there's also the potential for us using iron, which may also be present as rebar in these buildings, and that can have effect on radionuclide mobility as well. Next slide, please. Right, so how are we going to do this? I've got some field samples of some sediment that should be relevant to the Sellafield site from a quarry nearby to the site. I've been working on characterizing this, and we'll be using this for some sorption analysis. If you can click once there, Mark. And we're going to start small scale with batch experiments on the lab to kind of get a baseline of the fundamentals. And if you click again, Mark, we're going to slowly build up through columns, which simulate continuous groundwater flow. So you get closer to more real world conditions. And once again, Mark. And building up to field lysimeters, which are these meter scale sediment columns that are essentially left outdoors for months to years, and you can track how the radionuclides move through the sediment, where they end up, and how stable they're likely to be. And ideally, this research will aid industry in building safety cases for the in situ disposal of these concrete materials. Thank you.
Thanks, Jonathan. And I believe that's it. Thank you, everyone. Hi, Jenny.
Hi there. Thank you so much, everybody, for your involvement today. I've just put a link in the chat to the UKCRIC Doctoral Skills Network web page. It will be great if you're not already a member of the doctoral network, if you would be interested in joining us. We've got about 160 doctoral members and postdoctoral students that have joined us from the 15 universities and kind of a wider community that are linked to UKCRIC. There's lots of information about who the UKCRIC are and what they do, and you can see why that's relevant to your particular areas of research and kind of the energy sector as a whole. So it'd be great to see a few of you joining the network if you haven't already done so. But otherwise, I just want to say thank you very much for all those really interesting insights into your projects. It seems like there's lots of exciting things going on, and I wish you all the very best of luck with the work that you're doing, both the computational and the experimental, and all the other exciting things that you have going on with your trips to Taiwan and the USA. I'm quite jealous. So I hope this all goes really well. And thank you very much, Mark, for pulling this all together and introducing us to all of your students. And yeah, I just want to say thank you. If there's any questions that anyone has, feel free to drop me an email. I think my contact details are on the UKCRIC website, or you can put something in the chat on Teams. This webinar chat will stay available for a week or so probably. But otherwise, thank you very much and enjoy the rest of your afternoon and your Jubilee weekends.
Thank you, Jenny. Take care. Bye, Malik.